Hi, I'm Doug Hubbard, and this is How to Measure Anything, Finding the Value of Intangibles in Business. It's an introduction to why nothing is truly immeasurable. Everything that you ever thought was immeasurable actually was measurable. Now, you've probably heard or said some of these things in regards to a measurement. Maybe you've heard somebody say, we don't have sufficient data to measure that. Or maybe you've heard them say, this is too complex to measure. This decision is too complex. Or we can't really use historical analysis because every situation is unique. And how do we measure this when so many things affect it? Or how do we know we have all the variables? Well, in each of those cases, the implied alternative is, therefore, we're better off relying on our experience. Your experience is still just a model. You're modeling it anyway. The question is never whether to model. It is which modeling method is measurably less wrong. And we'll talk about why measurement doesn't necessarily mean perfection either. Let's talk about that first objection here. We don't have sufficient data. That's actually a very specific mathematical claim. When someone says they don't have sufficient data to measure something, did they do the math? Did they actually compute the uncertainty reduction they would get from a given amount of data, and they computed the economic value of that uncertainty reduction to determine whether or not that effort was justified? They're probably winging it. And this is what happens a lot when people object to various measurements. They're vaguely recalling some things they thought they learned in statistics in college, perhaps, but they're not quite getting it right. I'm going to talk about three reasons why anything ever seemed immeasurable and why they're all three misconceptions. I call them concept, object, and method, or .com if you want a mnemonic to remember them by. Concept has to do with the definition of measurement itself. It may not mean what you think it means. The object of measurement is defining the thing that you're trying to measure, understanding what it is, taking the ambiguity out of it. And finally, the methods of measurement. How do random samples work? How does statistical inference actually work, or controlled experiments? So let me address the concept of measurement first. This is key. For the better part of a century now, measurement did not mean an exact point. It's not a point value. The de facto use of the term measurement in the scientific community is a quantitatively expressed reduction in uncertainty based on observation. In other words, you start with a lot of uncertainty about some quantity you're interested in. You make some observations, do some trivial math, and then you have less uncertainty than you had before. Now, not only is that the de facto use of the term in the empirical sciences, it's the most practical use of the term for decision makers. So let's build on that a little bit. This whole approach of thinking of measurement as a reduction in uncertainty sort of implies that you needed to have an uncertainty to start with, which is the case here. So how do we start to quantify our current uncertainty prior to a measurement? There's actually been a lot of interesting work on this over the decades. It turns out that people can be trained to subjectively assess probabilities, and they can be trained to be pretty good at it. And here's what I mean by that. If I were to track all the times you said you were 80% confident, let's say for events that would happen by the end of 2020, and then I look back at the end of 2020 and I count up all the events that happened or didn't. Of all the times you said you were 80% confident, did about 80% come true? Of all the times you said you were 95% confident, did about 95% of those come true? If I tracked a large number of those forecasts where you're putting probabilities of anywhere from 50% up to 100% on things that you're assessing to be true or false, right? So if you had no idea, it wouldn't matter whether you said true or false. You would be indifferent between true or false. You'd say 50%. That's your most uncertain if you're saying that something's true or false about some particular forecast. And if you're absolutely certain, you'd say you're 100% confident. Well, over a large number of trials, if you're perfectly calibrated, you'd be right along this solid green line on this diagonal on this chart. We're comparing your assessed chance of being correct to the observed frequency of correct. Now, we've actually trained over 2,000 people in the last 22 years to be very good at subjectively assessing probabilities. And what we observe is when we give them their first exercise, the first test, the benchmark where they assess their uncertainty, People are systematically overconfident. This is consistent with all of the other research in decision psychology. People tend to put too high a probability on being right. They're not right 90% of the time when they say they're 90% confident. Even when they say they're 100% confident, they're wrong more than 10% of the time. When they say they're 90% confident, they have about a 75% chance of being right. But we also observe that after calibration, they can get very close to the ideal calibration line. In fact, almost entirely within the statistically allowable error for this size of this population that we're looking at. We've also observed that this training, which could be on just trivia questions, actually does improve people's performance on their real world estimates for things like project cost and the probability of winning some big contract, or what next quarter's revenue is going to be, or how long some R&D project will take before you can go to market. All of these are real world estimates that people are routinely asked to provide. Usually, not always actually, but what we do is we gather that information in a probabilistic form. If they don't know a number exactly, they don't say it's going to take exactly 18 months, they give us a 90% confidence interval. It'll take anywhere from 12 months to 20 months. And if they don't know for a fact that a competitor won't come out with a product earlier, they say, well, I'm 80% confident that we'll come out with it first. You're not 100% confident. So you can be trained to do that. We can also combine those estimates. This is still on the topic of quantifying your current state of uncertainty. Often you have to combine multiple experts when you're estimating something. There are ways to do that. And you don't just average everybody, even though that turns out to be kind of common. In fact, one of the more common methods is you get everybody in a room and they all agree on it. That might actually be the worst method, it turns out, for aggregating multiple estimates from different subject matter experts. But there are algorithms for doing it. And what's interesting is that the best algorithms are measurably better than your best individual expert over a large number of trials. This is fascinating. What do we do with these probabilistic estimates? We can't put them in conventional, traditional spreadsheets for a cash flow where we compute a net present value. In fact, what we do is we run a Monte Carlo simulation. This is a way we can do the math when you don't have exact numbers. And there's been some interesting research that shows that people who build Monte Carlo simulations appear to be better at forecasting. This appears to work because you're allowed to decompose your sources of uncertainty. And this is what Monte Carlos do for us. We decompose our sources of uncertainty. We don't know all of the inputs for the benefits or the risk of a new project. We put ranges and probabilities on them. And so we're going to get a range of potential net present values or ROIs. And we'll see that sometimes we lose money. And we can put a probability on that. If we see that out of 10,000 trials, there were 2,000 times we lost money on some investment, that's about a 20% chance of losing money. Now, there's a lot of ways that we can measure something, and there's a lot of very difficult sounding measurements. So I've talked about the concept of measurement, what measurement means, including how to set up the initial prior probability, your current state of uncertainty, so that we can reduce it further with observations. But we also want to talk about this object of measurement. This is important because a lot of very difficult sounding measurements are actually just a problem in how we define the thing that we're measuring. How do I measure teamwork? How do I measure strategic flexibility or quality or cybersecurity risk or the value of training? These are all things that we've heard. Innovation. How would I measure that? Collaboration. Each of these items are things that people have tried to measure, but they run into a wall, an obstacle, because they have a hard time even defining it. So I like to propose a few questions that helps them figure out what it is. First, what do you see when you see more of it? Have you observed that some individuals or teams are more innovative than other individuals or teams? Do you observe that some of them collaborate more? Or that some projects are more relevant for strategic alignment than others? What did you see when you saw variations in this? Almost anything you ever think of measurement is something you've seen real world variations of. Otherwise, you might not have even thought of the need to measure it. You think it varies, therefore you want to measure it. So what did you see when it varied? Identify some observable consequences. Once you figure out how you observe something, you're halfway to measuring it. The rest is trivial math. I also like to ask people why they care about measuring it. Why would you care about measuring innovation? Answering that question helps us frame the problem, and it helps us figure out how we might even start to measure it in the first place. Are you interested in measuring innovation because you're worried about which team to put in charge of a particular R&D project? Are you interested in the innovativeness of a city or a geographic region because you're considering putting your laboratories there and you want to be able to hire better people? Are you interested in measuring the innovativeness of an idea or design or patent because you're really forecasting how much money you think it's going to make? What do you mean by innovativeness? So, what we see when we see more of it, and then the why do you care question. Here's a few examples. How do we measure employee empowerment? Well, maybe employee empowerment really means less management overhead. Is that what you're seeing when you're seeing more employee empowerment? Maybe certain decisions are made more accurately and faster because you've empowered people at lower levels to make more decisions. How about information availability? Maybe that means the time and cost of searching is reduced, or certain costly errors in using the wrong information are less frequent, or customer relationship, increased repeat business. These are all examples of what people actually see when they see more of the thing they originally thought was intangible. And why do they want to measure those things? Well, you might want to measure employee empowerment because you're interested in investigating whether to implement a different organizational structure. Maybe you want a flatter organization and you're expecting some benefits out of that. Maybe you're calling this ambiguous group of benefits employee empowerment, but there are really a lot of separate things that you have to unpack. Likewise, for information availability, are you assessing a major investment in some new information technology, customer relationship? Are you considering a new help desk system, et cetera? Figuring out what decision you're trying to make and what you see when you see more of something helps you refine the object of measurement. Lastly, let me talk about the methods of measurement. No matter what you're measuring, assume the following until you prove otherwise. You have more data than you think. This is all about being resourceful. Don't give up so quickly, believing that you don't have data to measure something. You need less data than you think. When people do the math, they're routinely surprised at what kinds of inferences they can make from even a few observations. And finally, there's a good chance it's been measured before. I don't think that people in business nearly often enough take advantage of the fact that there's so much research on virtually any topic that's available right on the internet. All right. And I'm talking about published research, not just people's blogs. I'm talking about published peer-reviewed research with actual statistics behind it. When I talk about the methods of measurement, sometimes it's useful to just think about the variety of things that are routinely measured that might at first glance seem virtually impossible to measure. How did the Allies in World War II estimate the German tank production levels by month by a statistical analysis of the serial numbers of captured tanks? Not obvious, but possible. How does a marine biologist estimate the population of fish in a lake without draining the lake? Well, it's a random sampling method, but it's not an obvious random sampling method. It's catch-recatch is the name of that sampling method. My point is there's a lot of interesting techniques for measuring things that once you know they exist, you realize a lot more things are measurable than you might otherwise think. In fact, there's been some research on this. Daniel Kahneman and Amos Tversky did some research on this. Kahneman won the Nobel Prize in Economics in 2002, I believe it was. In economics, even though he said he never took an econ course in his life. And their research showed that people have strong intuitions about random samples that are wrong in fundamental respects. And this affects a lot of people's intuitions about what is measurable and not measurable, simply because their intuitions are incorrect about what samples can tell us. Here's one way to think about measurement. Imagine I made a chart where the horizontal axis represents my certainty in some quantity. So I have an uncertain quantity like the duration of a project or what next month's sales will be or something like this. And I can make some measurements. And as I take more and more measurements, I reduce my uncertainty about that quantity. As I go further right, I have less and less uncertainty, more certainty. My vertical axis is a measure of value or cost. It's a monetary measure. I've got two curves I want to plot here. One is the expected cost of information, or ECI. The expected cost of information rises slowly at first, but as I want to gain more and more certainty and get rid of that last little bit of error, the cost goes up quite a lot. Because getting rid of that last little bit of error, you approach, in some cases, infinite cost. to get rid of that last little bit of error, if it were even possible. Okay. There's another curve, the expected value of information, or EVI. That rises quickly at first, but levels off. It can't do better than perfect information. There's a finite limit to the value of information, no matter how much you get. So it has to level off. The shapes of these two curves, and you can work these out on an individual basis for individual parameters, you can find out that the biggest bang for the buck in a measurement tends to be early. That's what's interesting about this. A lot of times people might assume that if you have a lot of uncertainty about some quantity, you need a lot of data to measure it. In fact, just the opposite is true. The more uncertainty you have, the bigger uncertainty reduction you get from the first few observations. In fact, if you know almost nothing, almost anything will tell you something. That's the way to think about the math. Now, there actually is a way to compute that value on a variable by variable basis within large decision models. And we've been doing this for years. We've done lots of decision models, more than a couple of hundred, each of them having dozens or even a couple of hundred variables each. And we will find that some of the variables have very high information values and some have very low information values. That's not too surprising. But what I think is surprising is that the variables with the high information values are not what people would have guessed. People tend to spend their time measuring things that are statistically less likely to actually improve decisions. In the case of IT projects, they spend more time measuring cost than benefits, even though they're more uncertain about benefits. Within cost, they spend more time measuring initial development costs and less time measuring long-term maintenance and training, even though they're more uncertain about the latter. We call this the measurement inversion. We've observed this in every field we've ever done analysis in, whether it's about environmental policy or military logistics or R&D in biotech or aerospace. In each of these cases, people would have spent their time measuring things statistically less likely to improve the decision until we showed them what the information values were. That took them down a completely different path. So we've put all of this together into a process. This is a pretty high-level flow chart of the process I call applied information economics. It starts with defining a decision. All of the measurement issues that you're interested in are supposed to support a decision. Now, there's other reasons why somebody might want to measure something. They might measure it because the information itself has a resale value. That's one possibility. Or you might do it out of pure entertainment. But I'm going to start with the assumption that most organizations that want to measure things are trying to support decisions under uncertainty. We then model our current state of uncertainty about that decision. We can start with a Monte Carlo simulation, which is populated with those calibrated estimates I talked about. So at least trained estimators are estimating their current state of uncertainty. Once we have that, we can compute the value of additional information on every uncertain variable in the model. Then we can measure where the information value is high. Once we've done that, we update our model, compute the value of information again. We might go through this loop a couple of times. I rarely see it more than 3 times. A couple of times is pretty common. But once you've removed the uncertainty that's economically justified to be removed, then you can optimize your decision. That's how all of that works. So I'll just summarize by asking, what is your single most important measurement? The performance of your measurement instruments for decision making. What is the performance of your measurement methods? How much do they actually improve decision making? And this includes your subject matter experts measuring their performance at estimating things, certainly measuring the performance of the empirical methods that you're using, and even the quantitative models that you're building. There's a lot more to get into on all of this, but I wanted to give you some aspirational goals, maybe a few takeaways that you can think about, like, for example, just the measurement.com concept object method, and also that you have more data than you think, need less data than you think. And it's probably been measured before, no matter what you're measuring. So take all of that into account.